maybe I start over. Sorry. First of all, you want to get your graphing calculator out because that's going to really be helpful for this whole lesson. The other thing that maybe just to kind of put into your head for the whole lesson, I'm going to come over here and talk about SVA. So this whole lesson is going to kind of use this, but thinking about, we take the derivative of position to get velocity. We take the derivative of velocity to get acceleration. So to go backwards, we would do the antiderivative of acceleration to get velocity, the antiderivative of velocity to get position. So kind of just keep that all into your brain as we go through. All right, so looking at this first equation, the SDT, which is the derivative of position, so that's velocity, equals this equation. So go ahead and put that equation into your Y1 and graph it. And also when you go ahead to graph, anytime you're given a window for time, I would always put that into your X max and X min. So you want your X min to be 0, your X max to be 5, because that will narrow your window so you can only view what you need to talk about. So if we go ahead and graph that, it kind of looks sort of like this. And we want to find this value because remember, where V, our velocity is 0, that's where it changes direction. That's a really big, important concept to remember. Okay. So use your grapher to find the 0. So second, calculate, do the 0, do your before, your after, and you should find that the 0 is where time is 1.25. So you can see from 0 to 1.25, the velocity, because that's what we're graphing. This is the velocity function. The velocity is negative from 0 to 1.25 and positive after. So when we want to describe the motion, because V is less than 0, from 0 to 1.25, it's moving to the left. And then, velocity is greater than 0, from 1.25 to 5. Keeping in mind, we always want to stick to the time that they give us. Because the velocity is positive, maybe let me do this. Positive here, it's moving to the right. So this, we have covered all this before, but just connecting when velocity is less than 0 is moving left, greater than 0 is moving right. This is just using your calculator to find some of these pieces. Best way if you have a calculator available. Okay, so finding position, where it's actually at from displacement. It's saying suppose the initial position of the particle in example 1 is 9. So the particle is starting at 9. What is its position at time 1 and at time 5? So if we think about, we don't know the position function. We know the velocity function. So what we're going to do, now this is going to be really key. You will get points on your AP test if you include the initial position when finding your final position. But you only use it if we're looking for the actual position. So let's think about this. If I'm starting at 9, I'm going to add how much I've traveled in the first second. So would it make sense that I'm going to do the integral from 0 to 1? Because if we look at SVA, if I know the velocity to go back to finding position, that's where I do the antiderivative. from 0 to time 1, v of t dt. So just for video's sake, we'll just kind of shorten this up. But I would just math 9 this. So you already have the velocity function in your y1. So go back to your home screen and take 9 plus math 9, 0 to 1, using y1 dx. So if you plug all that into math 9, you should get 16 thirds is your fraction, or what is that? 5 1/3, or 5.333 repeating. So that would be for letter A. To do letter B, I would use my initial position of 9 and add on my displacement, or my from 0 to 5 of v of t dt. And so going back, doing the same thing, 9 plus math 9 to get your integral, plug all of that in, using y1 for your v of t. And it would be 44. So if we look back, notice this is in centimeters per second back in example 1. That means that it is traveled, it is at position 5.333 centimeters after 1 second. It is at 44 centimeters after 5 seconds. That's the position at each of those times. Okay, so now if we want to do total distance, this is really important. So let me just kind of do a for instance, and it'll be easier if you're in person here, but you're not. If I start, let me just make a little number line. All right. If I start at position 0 and I travel 2 steps to the right, and then I take 5 steps to the left, what's the total distance that we traveled? We traveled 7 steps as distance, but what's my final position would be at -3. There is a difference between distance and position. Position is always in reference to where you started from, but your distance traveled is always positive. So if we think about this, position we can get by taking 2 minus 5 to get our -3. But distance is 2 plus 5 to get our 7. So a distance, we want to calculate each piece separately. We have to calculate our positive motion differently from our negative motion. All right, so we can do this a couple of ways. Going back to, we're still talking about example 1. So if I want this to be all positive, does it make sense that I want to reflect this portion above the x-axis where I have all positive values? Notice 0 to 5 this way, there would be some positive, but this area here would counteract some of the positives. Where this is all positive, this would be negative. So what we do, and what's really nice is with the calculator, we can reflect it above by taking the absolute value. So we're going to calculate distance traveled by taking the absolute value of the velocity from 0 to 5. All right, so this time I want you to math 9 before you put in from 0 to 5. Don't put the function in yet though. the first thing you have to do is the absolute value bars first. So you want to go to math, over to number, and number 1 is abs. Then put your y1 in here, d, and yours would be dx on the calculator. And just plug it all in, and you would get 42.59. I'm probably using the book's value, so I don't have the 4 decimals. And this would also be centimeters. So this is what you want to do if the calculator is available. If you have to split it up, because this would be below, you would have to do the opposite from 0 to 1.25 plus, see how you have to divvy it up from 1.25 to 5, and you'd get the same thing. This would make the negative value positive, then we'd add on the positive parts, and you would get your final answer of 42.59. All right. For the general strategy, I'm doing it with you. The general strategy for modeling, we can actually find these in a couple of ways. Do not write all of this down. What I would just do is do a Riemann sum of values is one of your options. You could write a definite integral and you can evaluate. So I'm going to tell you I would not use a Riemann sum unless you're asked to do a Riemann sum, but you're always going to get points for writing a correct integral, and then obviously you want to make sure you can find the right answer evaluating it. All right, example 4. So modeling the effects of acceleration. So a car moving with an initial velocity. Initial velocity is v of 0 equals 5 miles per hour and accelerates at a rate of 2.4 t miles per hour for 8 seconds. All right, so let's think about, so it's saying how fast is the car going? So do you see how this is just a step up from the SVA that we were doing before? We're now going from velocity and back and forth with velocity and acceleration, where the first 3 examples were going back and forth from position and velocity. All right, so if I want to find v of 8, I need to use my initial velocity of 5 plus, since this was at time 0, I'm going to integrate the acceleration. So I'm going from acceleration back to velocity, 2.4 t dt from 0 to 8. So we get our initial from here and our final from here. All right, so this we can actually do by hand. This one's not terrible. So this is 5 plus the antiderivative of 2.4t is 1.2 t squared from 0 to 8. Now, make sure you're keeping all of this separate. This is the, let's see here. This is the only part of the integral, okay? All right, so this 5, I'm just adding on, plug in the 8 so I can do the top. So 8 squared is 64 times 1.2 is 76.8. So my velocity at time 8 is 81.8 miles per hour. All right. So then we want to do the same thing for letter B. How far did the car travel? Okay. So this is saying how far did it travel? That's going to be our distance. So now let's think about this. Here, let me make a little bit of room. No, I'll just go down. Hang on. So now we want to, if you think about our velocity function, because this initial velocity here, we can take our acceleration function, 2.4t, and add on, that's like our constant, plus c. We can use this now to go backwards to distance. That I can find. This represents time 0. So now we're going to integrate to find distance from 0 to 8 seconds. And I'm going to actually use the absolute value. We're going to do this on a calculator. This will be nicer. Plus 1 point. Actually, if you think about 5 plus 1.2t squared, that's just your parabola up 5. This is all above the x-axis, so there's nothing that's going to be negative, so we can actually just do the integral by hand, but you can check it on the calculator. But that'll be 5t plus, that'll be t to the third, so 1.2 divided by 3 is 0.4 from 0 to 8. And if I plug in all of my values, I get 244.8. All right, so this is miles. Oops. Now we have to be careful because think about how this was miles per hour, our velocity function, but we were also talking about 8 seconds. So now we got to convert it from hours into, this is per hour, miles per hour. So now I got to convert 1 hour into seconds. I'm going to use my little T-chart. So we have to divide that by seconds because we're talking about 8 seconds here. All right, so then we end up with 0.068 miles. Okay. All right. Consumption over time. Okay, this one's about the easiest thing ever. So, first of all, in the spot for consumption over time, think about how the integral just calculates the net change or total accumulation. Basically, think about this. You integrate a rate. I'm going to make that a t. If you want to calculate an amount. I talk about this all the time. This is really important. Recognizing that you are starting with a rate and you need to find the amount of something, you just need to integrate. Just use math 9. So for example, our potato consumption from 1970 to 1980, the rate of consumption was C of T equals this, millions of bushels per year. So per year is showing that it's a rate. It says how many, so see how that's a rate, but we want to know how many bushels to an amount. So we're going to integrate our function, 2.2 plus 1.1 to the t. Now let's think about this. This is the rate from 70 to 80. What would our numbers be if we're going from 72 to 70 to beginning of 72, right? So from 1970, 1971, 1972, so that's the beginning of the second year, to the end of 73. So that's all of 72, all of 73. So 4 would take us to the beginning of 74 or the end of 73, okay? So we integrate a rate, just math 9, put that in. These are always going to be calculator questions. These are beautiful. So go ahead and just math 9 that. 7.066. This is going to be really important though. This rate is in millions of bushel. So make sure you're reading if it's in thousands or millions or whatever it might be. But For this, it's just important to recognize that you're going from a rate to an amount and then just plug into Math 9. So that's really nice. Okay. So sometimes we're given, and I do see this on your free response questions, where they might give you, instead of giving you an equation, they may give you a graph. And so you've got to use a graph in order to do this. So it says from noon until 6, the rate at which people enter an amusement park is given by the graph E of t, where t of 0 corresponds to noon and t of 6 is 6 p.m. So this is 6 p.m. And it says if 3,000 people are in the park at noon, you have to recognize that's an initial value. So at time 3,000, there are 3,000, or at time 0, noon, there's 3,000 people. Oh, then people are also leaving at 50,000 here. Hang on a second. Oh, there. I needed to get my L of t. They're leaving at this rate, but they're entering at the graph. And this is our initial value that we're starting with. It says how many people are in the park at 6 p.m. All right. So does it make sense in general? We're starting with 3,000. Then we're going to add our entering. So if the graph is our integral, we have to integrate E of t. We're going to add the entering. Then we're going to subtract the leaving. So then we have to do our integral of our leaving, and that's going to give us our total. The initial value, adding who enters, subtract who leaves, that's going to give our total amount. All right, so to figure out our entering, we have to integrate the graph, which means we have to find the area between the graph and the x-axis. So I'm just going to notice this is a trapezoid, that's a rectangle, that's another trapezoid. And when you calculate your areas, that's 1,500, this is 600, and this is 1,100. So I'm going to use the area under the curve to find the integral of entering. So my initial value plus all the people who enter, 1,500 plus 600 plus 1,100. Then I'm going to subtract off my leaving. So this one, I'm just going to plug this equation in, Math 9. Just plug that in from 0 to 6. And if you Math 9, you get 2,106. So if we add all these people and subtract off the leaving, I get 4,094. Now, it says rounded to the multiple of 100. So what's your nearest 100? I'm going to say that's 4,100 people. So make sure you're reading your directions and answering your question to the best of your ability. All right, so now this is using a table, and it says they want us to do, all right, a pump is connected to a generator. So using this table, it says the rate at which the pump operates is recorded in 5-minute intervals for 1 hour. How many gallons? So the table is a rate. So we're going from a rate to an amount. So we need to integrate. So we're going to integrate our pumping rate. So I'm going to say my rate of t dt from 0. Now, we want to, during the hour, and notice this is in, time is in minutes. So how many minutes in an hour? From 0 to 60. So it doesn't you don't see it here, but we're actually going to use a trapezoidal rule. So if we do our trapezoidal rule with this table, let's remember first our h is our change in x. And in this case, that is 5. So the trapezoidal rule, we use h over 2. So in order to estimate this integral, I'm going to use h over 2. Then I need one of the first. I'm going to double each middle. So 2 times 60, blah, blah, blah. And then I only use one of the last and plug all of that in. And we get 3,582.5 gallons. And that's final answer. All right, the gopher problem. All right, I think my bell's going to ring pretty soon, so this is going to be you'll want to maybe just look at the last two in your book, or we'll talk about it when you come back.